Okay? It's quite, so it's also difficult, but I think you're doing, so I'm assuming that you're not getting the solution from the books. Okay? If you don't do it like this, I think you're doing fine.
What about not getting the solution at all?
Huh? What?
What about not getting the solution at all?
Very good. Okay?
I forgot something like.
Jesus, it's a disaster. You did not come to the lectures. Then
Sorry.
you forgot things. Shall I start? I start. So you know that yesterday we discussed about transition between levels of the atoms. Okay? Now, transitions occur because you just shine your atoms with some radiation, electromagnetic radiation, and due to the interaction of the electromagnetic radiations with the atoms, it is possible that there will be transitions from one state to another state. Okay? Now, we saw also that these transitions very strongly depend on the frequency of the periodic driving. Right?
Okay.
So, if you choose a frequency which has some mismatch, is strongly detuned from a certain energy difference, then there is no real effect. Okay? So in order to have a finite probability that an atom or some jumps from one level to another, then you have to choose the right frequency. Okay? Do you know that not all the transitions are allowed? If you do not answer, next time you will sit here, okay? So then you move there. So you should answer.
We just heard about it.
Okay. So you heard about it. The question is, do you know that, so if for instance you apply, so what are the hydrogen, the levels of the hydrogen? How they are classified? The quantum number, this you know.
Yes.
So first the principal quantum number is n. And this goes from -10 to?
Goes from 0 to infinity.
Okay, so it's not -10. Very good. Okay? So you have, then you have the other quantum number which is called L. Huh? L. Okay? Now, it goes to
Minus n to n.
0 to n minus 1. Okay? Then you have another quantum number which is m. Okay? So you take the level 1s and you take the level 2d, and m it's from something to something else. Okay? Is this transition generically allowed or not?
No.
No. So only certain transitions will be allowed. Do you know this? Okay? Now, the exercise that you have to solve is to understand why, so I will specify, don't worry. You have to specify what transitions are allowed and what transitions, so why certain transitions are allowed. Okay? So, as compared to what we did so far, since you were absent, either you speak with them or you just come to me and you ask me details, okay? We have to go in some more details. So we have not a generic periodic perturbation. We will have an electromagnetic wave. So we have to specify the generic case that I discussed previously to the case in which there is a electromagnetic wave interacting with the atom, right? Once I specify this, and this is your exercise, I will explain you the main steps, okay? But it's good that you do it yourself. Then you will see that under certain assumptions, the matrix element, you remember that what we solved was that the probability to have a transition was something which was peaked at the frequency times there was some matrix element squared. Then we will see that when we just go in some specific situation which we want to describe the interaction of electromagnetic wave with an atom, then we will see that, so we'll consider hydrogen atom, okay? So we will see that only certain matrix elements will be different from zero. Is it clear? So you will make a step forward in understanding a specific case which has, however, overwhelming importance as you can understand the atomic spectra. So, the goal is to compute the Fermi golden rule for this particular case. If in principle, if I want to study the interaction of electromagnetic field with a quantum system, in principle I have to consider both the system and the electromagnetic field as a quantum systems, okay? Now, because you know that the quanta of the light are there. How do you call quanta of light? Photons, okay? So in principle you should write the full quantum mechanical problem of photons interacting with matter and solve the problem, which is too difficult. If you have just so you have a quite intense radiation, then it is enough to consider the radiation as classical. Okay? So you have a classical electromagnetic field which interacts with a quantum system. Now, the first step is to write down an electromagnetic wave. So what is an electromagnetic wave? rewind. What is an electromagnetic wave? Don't say we heard about it, because it's not a good answer. Now, look at me. Eye contact, okay? Don't just So, do you know what is an electromagnetic wave? Yes or no? Yes. So the next question is that if you know, why are you silent? Because this is a secret that we should keep, huh? Or you can share your knowledge with me. I will be delighted.
EM waves are the solution to the...
No, but I want a simple answer. So what it is? What is it? Is this electromagnetic wave?
No.
No. This is a chalk going up and down. Okay? Good. So just give me very simple explanation of what is electromagnetic wave.
Excitation in electrical. I don't know what's the
Exactly. I think electric excitation and magnetic excitation is...
Now we are going close.
And it's
Very good. We are going close. Now, okay, what kind of excitations?
wave excitation.
Wave, what is a wave?
An object that satisfies.
No, a wave is not an object.
I mean the.
It's energy.
There is energy, but what is a wave? So, I'm a little boy, okay? And I come to you and say, okay,
Wave is
hi, Uncle Michael, or can you tell me what is a wave on the sea?
It's an excitation that travels
I
through
mean,
space.
if you talk to a 5, I mean,
Okay, so it's
why it's an excitation?
transfer of energy from the molecules from one end to the other of the medium.
Okay, no. No. Okay, so you want to speak with, okay, I'm not anymore a kid, okay, because if a kid comes to you and you start talking about this, he gets bored, okay? So I'm an old guy, just tell me, what is a wave? So what is a sound wave? Okay, so I want to exclude stationary wave. So wave, for instance, when you play guitar, do you have waves
Yes.
on the strings?
Yes.
Why do you know that you have waves?
because it produces the sound. Because they are vibrating.
Yes.
Because?
They are vibrating.
So it is a vibration. In this case, it's stationary or it's propagating.
Stationary.
It's stationary because you have points in which, so what is vibrating?
The deviation from the equilibrium is
Very good. So there is, in this case, there is the amplitude, which is variation, which is, in that case, it's a perturbation which is changing how? Periodically in
time.
time and space. Right? So sometimes it's like this, sometimes it's like this, okay? Now, the sound, what is, so you know that this perturbation can propagate, can be stationary, so let's consider the sound. What is, there is no string, okay? So what is a sound? Is it a wave or not?
It is a wave of inhomogeneity.
It's a wave, okay? What is changed? What is the inhomogeneity?
The density of the.
So it's the kind of wave related to compression, decompression in a certain medium. Okay? So a wave in general is a phenomenon which takes care in a given medium, or so what, and it is associated to the periodic modulation in space-time of certain quantities. Okay? Do you agree with this or not? Okay. So, electromagnetic waves are these are called electromagnetic. So you should tell me. So since I'm using wave, we agree that it's periodic perturbation. So let's consider that it can propagate. So you should tell me where it can propagate, what is oscillating. So
It propagates through space, is periodic in time.
yes.
And
So does it need a medium to propagate?
no,
No. So it can propagate also in.
vacuum.
Okay. Good. So what is propagating?
Electric field and magnetic field.
The electric field and magnetic field, which oscillates in space-time. Very good. Now, how do they oscillate? So, can you define a direction propagation? No? Yes.
Right hand rule.
Huh? What?
Right hand.
Right hand rule.
Pointing.
I mean, if you play with a laser, then you just are pointing somewhere. Okay. So the way.
If
This
the
is the
laser-
electric field, this is the magnetic field, they are perpendicular to each other.
Okay. Now translate this in language. Okay.
If the wave propagates this.
Suppose I am an alien and I have no hands. Okay, so I'm only able to listen to you.
The electric field.
Or I have no thumbs. So then you have to find a way to so you cannot do it like this. So it propagates
A wave.
in a way. I mean, it propagates in a given direction with the electric field and the magnetic field oscillating.
Perpendicular to this direction
Plane.
to each other.
Very good. So you knew it. Very good. So should I get an extra salary just to pull out the information that you have in your mind? Huh? No, you should say it. Very good. So because of this property, electromagnetic waves are called longitudinal waves, right? No, transfer. The oscillation is not along the direction of propagation, but is transferred to it. Right? Okay. So we say that we should write, so to describe an electromagnetic wave, then we should write down the electric field and the magnetic field of the wave. Right? Now, why do we need both the electric field and the magnetic field?
Because they are both components of the.
Right? And so, if I'm an electron with a given spin, so I should describe the interaction between myself and some impinging electromagnetic field. Okay? Now, okay? So that's why we need it. So we need we need first how to describe a wave and then how to describe the interaction. Let's consider first the wave. So just consider, so I want to write the vector potential, okay? the vector potential okay? I just choose of this form. This describes, you see, it describes something which is oscillating in space and time. Now, just fix this gauge. Now, how do I compute the electric field from the vector potential? If I give you an the vector potential, how do you compute the electric field?
Time derivative.
Okay, so E is,
Was it with minus sign?
okay, but this you should go back and check. So it's minus over C D. Okay? Then you want to compute what?
It's Gaussian units.
GGS, CGS, yes. Okay? So, and the magnetic field is what?
Curl of A.
Very good. Now, verify that all this is, so if you want, you can take R equal 0, Y 0, for example, and verify that this propagates along Y and the electric and magnetic field oscillates. So I have 0 component along the direction of propagation. Just verify, okay? Now, this is one thing. Then I have to write down the interaction between the quantum system and the electromagnetic wave. So you see that this is a periodic perturbation, okay? The only difference, we should be careful here, is R, but it's just periodic. Huh? Now I should write the interaction between an atom and, how should I write? So let's consider hydrogen atom, okay? So first the kinetic term. So the kinetic term is what?
1 over 2m p minus the momentum minus E divided by C vector potential squared.
So I take a negative charge, so E over C. Very good. Okay? Then I have potential energy. Then there is another term. So I'm forgetting about relativistic correction. We forget. Now, if this particle has a spin, then in principle I may have another term. No, this is
Magnetic
relativist.
field in spin.
Yeah, so it's just B dot S. Okay? I'm disregarding. So I will have plus this is the ball magneton. Hmm? I expand this, okay? Then you see that I get the first term, the square of the second term, and here I get two terms. And here I should be careful because I get P dot A and A dot P. P dot A is just the divergence of A. But I'm choosing this condition, so the only thing I need is, okay? Now, can you tell me what are the perturbation terms?
Do we keep A squared?
Yeah, for the moment we keep it.
And the perturbations should be terms having vector potential and magnetic field.
Sorry. So, tell me. You just tell me. So, one term is this one.
Next one, and magnetic field.
Okay? So, H0 is what? Okay? And V is? Okay? So now, basically, you have all the information. This is H0, and you know all the eigenstate. The first exercise, so I assigned you some exercise about what? About with the hydrogen. Ah, yes, about the Vardenberg faults. Okay? Where you used the eigenstates and eigenvalues of the hydrogen atom. So now there you have two, so you have to multiply and some way. So here you have one atom, so you know all this, right? Okay? This is the perturbation here. Now, out of the perturbation, then, okay, you can keep all the three terms, okay? But a good way to simplify the thing is to see if these three terms will contribute at the same level, okay? So the only thing, so the thing you can do is just evaluate, just have an estimate of this term as compared to this term. Okay? Just to give you you have to evaluate the estimate. So now I will explain you what you will get, what you should get, how to do it, and then we check it together. Okay? So, B and A are related by this relation. Okay? So if you have, let's do simple thing. We just take A0 in one direction. Okay? So, and it's oscillating along Z. So it has a component only in one direction. Okay? Now, so you know that the amplitude of this is A0, and the amplitude of B is just A0 times, so you have to take the gradient, so you get K times A0. So you have to do this. Okay? So you have an estimate for A, so the order of magnitude of A, B, A squared. Then you want to understand what you have to put here, P. So, do you have an idea of how to estimate P? For a nitrogen atom, what is the typical dimension of, so what is a scale which characterizes an hydrogen atom?
Bohr.
Bohr radius. From Bohr radius, can you compute some associated momentum?
H bar over A0.
Very good. Okay? So you just substitute all these things and then look at the ratio between the terms, just to see the order of magnitude. Then, if you do it correctly, then you will see that these two terms are much smaller than this. In particular, this term compared to this is related to the ratio of the Bohr radius divided by the lambda, the wavelength of the. So you will find that if you call this 1 and 3, 3 divided by 1 will scales like Bohr divided by lambda. Okay? I mean, it's not okay that you have to understand it now, because you have to do it. But this is very important so that you start understanding what does it mean to have an idea of the various order of magnitudes. Now, if you just substitute typical wavelength for, I don't know, visible light and the Bohr Bohr radius, sorry, this will be much smaller than 1. Okay? So the next approximation is to say, okay, as you suggested, we drop this. So you can check that also this ratio is scales like this. Okay? Michael, you do not seem to be happy.
I'm happy with the middle one because it's E squared divided by C squared, which is really small.
No, this is not the good, because E squared, so how do we decide if something is small or not?
It has to be smaller than some energy.
Like
No,
first term compared to second term, I'm okay that the second one is way smaller.
how do you know?
First of all,
No, it's correct, but how do you know? So what do you have to do?
the first.
Look,
Okay.
I think you are right, but I would like to insist on this. You cannot just simply see this, because this is a number, it's dimension full. In order to decide if something is smaller than something else, then you have to you have to compare the same scale, so you have to compare typical energy with typical energy. Okay? Go ahead. So you cannot compare this, I would say.
Well, from this first equation where we define the vector potential, if we use that the characteristic momentum, if we can call it, is h bar omega divided h bar divided by
exactly. Then you compare and then you get something similar.
Then if we compare first term to the second term, it can be seen that second one is smaller.
No, you have to, exactly.
Yes.
But it's the same here, because you have to substitute.
Instead of S, like spin.
Now S is of the order of 1.
Yeah.
It's 1/2, whatever.
It's order of Bohr magneton times.
No. Right, so you just substitute and you just check it.
Okay.
Okay? But you see, in both cases, since here there is B. B is something like,
Of order of A.
no, lambda. There is a gradient here, which is important. So B is something like K times A. But K is 2 pi over lambda.
P is of order A divided by Bohr magneton.
Yeah, no. That's the point. It's not. No, because also the wavelength will enter.
Ah, yeah.
Okay? So when you take the gradient, or the curl of A, the magnitude,
Will be A divided by characteristic K.
which is lambda, this is the K, that's the point. This is the K of the radiation. It's not the K of the atom. Okay? Which is exactly the point. You can drop these two terms as compared to this, because the wavelength of the impinging radiation is much larger than the typical wavelength connected to the atomic system. Okay?
So roughly speaking, this P operator that we have.
P is the something of the atom.
Atomic scale, and this gradient is the scale of the electric field.
Yes.
Okay.
Okay?
Okay.
Clear? I will do an experiment. When you do the exam, okay, I will sit down saying nothing for 6 hours. I just look at you, okay? Do you agree that you will become very nervous? Huh? Because when you talk to somebody, then you try to get the information, the feedback, right? Am I saying something stupid, or am I brilliantly describing advanced quantum mechanics? Okay, so you need some feedback.
Is it really, I mean, in order of magnitude, yes, we can omit the second term and the third term. However, our problem is that we want to prove transitions, be that S, for example, degenerate transitions.
No, here there is no degeneracy.
But we have hydrogen.
For the moment, I'm considering non-degenerate levels. Okay?
Okay.
Let's not.
It will cause splitting.
So huh?
It will cause.
Oh, sure. They play a role, but if you want, I can complicate your exercise.
Okay.
Oh, this is an exercise.
That's a nice suggestion. Tomorrow I will come up with. Okay. I want to consider a symbol, not symbol, but still. Very good. So you can drop those two terms. Okay. Now just take this. Let's simplify to one direction or another. It does not really matter. Okay. So I want to take this as A0 times Z direction and propagating along Y.
Do we take A0 as real or it doesn't matter?
Now you can take it as real. It does not really matter. You can take it. Because if you don't take it as a real, it means that you are shifting here by a phase. Okay?
Yes.
Which means that you are just redefining the time origin, so it's not really matter. Okay? Good. So at the end, you should end up doing your calculation to get something like that the Hamiltonian is like H0 plus E over MC A0, then you have E to the I this, okay, and then you have Z dot P. Okay? So this is what is written here, okay? These are the two.
It will be just cosine, right?
It is cosine, yes. But you have to remember that when you are on resonance, what it counts is only the resonant, only one of the two exponential. The counter rotating does not play any role. Okay? So you remember that if you had two terms, you get something like n omega I minus plus minus omega. Okay? So one which is divergent is much more important than the other.
But it's also depending on space coordinate.
Yeah, now let's just a second, okay? Just a moment, okay? So next question is space coordinate, right? Now, what is the range of variation of Y for an atom? So what is the typical size of an atom? Of the hydrogen atom?
Angstrom of...
You already used it's the Bohr.
Yeah, twice for...
The Bohr twice, it
Yeah.
does not matter. Bohr distance. Okay? Now, K times the Bohr distance, okay, tells you essentially how this phase factor changes in the region you are considering. But this is again AB over lambda. Okay? So if you have a wavelength which is much larger than Bohr radius, then you can consider this as almost a constant in the region of the where the wave function is different from zero.
Can you repeat that again, please?
Yes. Now, we agree that there is also a space dependence. Now, I would like to understand if this space dependent. So we learn how to do perturbation theory by just considering the time dependence. Okay? So here there is also a space dependent. Now the question is the space dependence important or not? What I'm saying is that since the wavelength of the radiation is much larger than the dimensions of the atom, then on this scale, on the scale of the Bohr radius, I can consider the system independent on space. So we are on the, so is the hard flat or curved? So the heart is, so this we know, we heard, right?
It's flat, of course.
So be careful. Okay? Now, locally, do you feel the curvature?
No.
Why don't you feel it?
Because it's
Why don't you feel it? So just give me a scientific definition.
Because the curvature is really big compared to this.
Right, so you compare the scale over which you feel the curvature with dimension, right? So if you want to see something, you want to describe, I don't know, horizon or other things, then you start seeing that there is a, right? So now it's the same. So you have a perturbation which is huge as compared, so suppose I am like a Bohr radius, okay? If there is a variation which is on the scale of few kilometers, okay, I will not see a variation, I just see something flat, right? So this means that I can forget about this term, okay? And now you are in your comfort zone, because this is exactly the same Hamiltonian perturbation that we studied. So here omega t plus e to the minus omega t, right? The only thing which changes is this term here. So we are specifying that this is the interaction. Now, in order, so what we study is that in order to determine the transition, then you have to apply Fermi-Golden rule. Now, if you remember, in Fermi-Golden rule, there was 2 pi over h bar, which we know how to compute. It's 2 pi over h bar, period. Then there was a delta function of the energy difference minus h bar omega, and in between there was what?
Matrix and matrix.
There was a matrix element squared. So the only, after all what I told you, the only thing that remains to be computed is the matrix element squared. So you have phi 0 of n, so I just put pz because we are taking the z direction, okay? So we have to compute this matrix element, okay? Now, a trick to compute this matrix element. Just try to do the commutation relation between z at h0. Okay? Just do it. If you do this, then you will find something which is proportional to pz. So instead of using pz here, you just put z, the commutator of h naught, but then it's nicer, because then the application of h naught on the right and on the left, you know how to do it, because these are eigenfunctions. And then it remains to compute something like phi 0 n z phi 0 I. These are the eigenfunctions that you studied. Then you have to prove that these matrix elements are 0 unless L prime differs from L by 1 and M the quantum number m is the same. Okay? So this you have to do, but I explained you everything, I hope. Questions? No questions. Can I change subject? Yes.
Sorry.
Yes,
Well,
yes.
Don't erase the perturbation part, the V part. So we have first, second, and third term, right?
Mm-hmm.
The most, I don't know how to say, the smallest part of this, out of these three, is the middle one.
I don't know. Why? Could be. How do you decide? So the only way you decide is the following. You just compare this with P, you just take H bar over A bar, okay? And you compare this, so you have E over 2 MC A0 H bar over A bar with so you have to compare this. I mean, just do it. And then this depends, sorry, you see that this depends on the magnitude of the field. Okay, so if you put, so you see that, okay, so you find some, so you just decide when this is of the same order, and then you decide, you have to check what type of magnetic fields and electric fields will satisfy this. Okay? Now, if for typical experiments or the system you consider that the amplitude is such that this is not satisfied, you drop. Okay? But I don't think you can just decide. Okay? Okay.
Yeah.
Change subject. Adiabatic perturbation theory. Adiabatic expansion, let's call it. So when you did the exercise with the perturbation, which was like e to the minus t square over tau square, then you saw that if tau square was very large, so the modulation was gentle, then you saw that the probability to excite the system from the ground state was smaller and smaller. Okay? Now, this is something which is very general, and it is related to the fact that if you take a system and you change the time dependence of the Hamiltonian slowly, what does it mean slowly? I have to tell you in a while. Then the system tries to adapt to the local conditions. So for instance, if you have a tray with glasses, okay? And then you have to put them there. So the glasses are full of water. How do you do it without spilling the water? You move slowly, right? If you do like this, then you make a mess. So if you do slowly, then hopefully you manage. Okay? So what we are going to see is kind of this fact on a quantum system in a bit more formal way. So the question that we would like to understand is there a better description or starting point to describe a system which has an Hamiltonian which changes slowly in time? What does it mean slowly? Just to give you a rough idea, that the time scale of the change should be much longer as compared to h bar divided by the energy gaps. Okay? But this we'll see. So, Schrödinger equation, okay? So we consider the Schrödinger equation generically, right? Now, as I told you, if we do something, so if H is time independent, if you start from an eigenstate, where does the system, how does the system change as a function of time? It remains in the same eigenstate. Okay? Now, we also saw that the system does not like to have transition if the evolution is slow. Okay? So, probably a good starting point in this case to describe the system. You remember that in perturbation theory, we choose the right basis on how to construct the perturbation. So we choose, for instance, the basis that diagonalize H naught. Now here, in the example of the glasses, okay, let's keep this example of the glasses. If I start here, this is my ground state. When I do it slowly, this is what? This looks like the local ground state where you change the parameters of the Hamiltonian from here to here. Okay? So I would like to formally write down this idea and introduce what is called the instantaneous eigenstates. The instantaneous eigenstates are, let's see, I would like to use the same notation. So, yes. So H of t think this is yes. So I define an artificial eigenvalue equation at given time. Okay? So for each time I have an Hamiltonian, and so I can define this eigenvalue equation. This n of t have nothing for the moment, nothing to do with the dynamics. Since you have a time-dependent Hamiltonian, this is the equation that you have to solve. Okay? This is not this one. It is this one. Is this clear or not? I want to hear a convinced yes from each of you.
Yes.
Yes, yes.
This is not each, some. Okay. Yes? Yes? Amel?
I don't know what is n of t.
Yes. Okay.
Yes.
I just take a given time. This is a trick. At a given time, the Hamiltonian is h of t. Then I find the eigenstates and eigenvalues of h of t. So this is a Hermitian operator. I can diagonalize, right? And I call this eigenvalues n of t. Since in each t, h changes, also n will depend on t. I'm assuming that the system remains always, is non-degenerate and will remain non-degenerate. Esdron will generalize to the degenerate case. Okay? I am assuming that n, so n is just labels the eigenvalues. Okay? I want to stress, n does not, it's just a mathematical trick, okay? Because the dynamics of the system is described by this equation, not this equation. Clear? What I would like to do is, however, to use this as a basis. Okay, this is a good basis, right?
Yes.
So, sorry. Yeah. So, since this is a good basis, I would like to write psi of t, the real evolution of the system, as sum over n of some coefficients a n of t Okay? So, since this is a basis, I can write this as a tilde of n of t times n of t. Sum over n. Okay?
Can I have a question?
Yes?
What can we say about the orthogonality of the states?
So this is an Hermitian operator. So the eigenvalues are orthogonal.
If they are taken at the same time.
This everything is the same time.
But
This
if-
here time is a parameter.
Yes, but if we bracket n of t and n of t prime, then what should we do?
Whatever. but we don't care. The only thing I'm saying is that I can use at any time the basis, and the basis change in time. So let me ask you the following problem. Okay, I just use is convention. Now, suppose that you solve a classical problem. Actually, this is part of the exercise I gave you. So, that for instance, you have a rotating magnetic field. Now, you just change reference frame such that you take a reference frame which rotates or moves in a certain way, so that you can do it. And so, in different times, they change. So at each time, you're just using the orthogonality condition. But of course, if you take two different, if you take two different times, they are not orthogonal. But you don't care. It's that you are using a reference frame which change in time. Am I allowed to do so?
Yes.
Okay? So far, it's a choice. You may tell, okay, you're an idiot, right? The only thing I'm going to show you tomorrow is that with this choice, things will simplify. Now, I did not use this, but I just used this. I just put these phase factors. For the moment, it's just a choice to simplify the equations, okay? But for you, either a tilde or this is the same. Okay? Now, suppose that psi at time 0 is n bar of 0. So the system is in a given eigenstate. Okay? Now, if you choose this formulation and then you take a time independent Hamiltonian, then we know that the system should remain this eigenstate by construction if the Hamiltonian is time independent, which means that we will find that this an, if it's 1 at the beginning, will remain 1 for any time. If it was 0 at the beginning, will remain 0. Okay? If you do this choice, it means that an of 0 is equal to delta n bar. Okay? Now, what I'm going to show you tomorrow is that if you make this choice for a slowly time Hamiltonian, you don't get that an of t is a delta function, but it will deviate just a little bit from this. Okay? So then it turns out that by using this instantaneous basis, we are all the time quite close to what exactly happened. If, of course, so this is only important if the perturbation is low, because if it becomes fast, you can choose this or another basis, but there is no real advantage. Okay? Like in perturbation theory. In perturbation theory, you choose to expand the state in basis of H0, because then you can compute the correction at some order. Okay? If the perturbation is not small, nothing dramatic happens. If the perturbation is not small, then you can still take the basis of H0, but it's useless. It may be useless. Okay? So tomorrow we are going to do this expansion and then you will see what I mean. So let's stop here. So is there anybody want to ask questions? No? Okay, let's go. But what happened? Why did he died? So, but I have a curiosity. But does this camera moves? Because they say that in principle should move. Okay.
There are two levels, and two levels is that you can always get them into two-one matrix. Two-one is vector. Okay. Fazio gave you a paper about entanglement. Did he give you also? When you pass the assignment, he will give you a paper of entanglement. He told me that.